Everything you think you know about space is probably wrong. Wrong in a way that goes far deeper than the corrections Einstein made to Newton, where the old physics still works fine for everyday situations. The kind of wrong we're talking about here stops physicists mid-thought and makes them stare at their equations because the mathematics keeps insisting on something that human intuition flatly refuses to accept. Picture where you are right now, sitting in a room or lying on a couch or commuting somewhere with headphones in, and notice that space surrounds you in every direction. Three-dimensional space extending up and down, left and right, forward and back. Space you can walk through and fill with objects and measure with a tape measure. This seems so obviously true that saying it out loud feels almost pointless because, of course, space is three-dimensional, and, of course, more space means more room for stuff, and, of course, a bigger container can hold more information than a smaller one. Except that last assumption might be completely false, according to some of the most carefully developed theoretical frameworks in modern physics. The amount of information that can exist in any region of space might not scale with volume at all, and instead might depend on something else entirely: the surface area, the walls, the boundary surrounding that region. This is the holographic principle, and over the next 2 hours, I want to walk you through one of the strangest ideas to come out of theoretical physics in the past 50 years. Space and time, the very fabric we assume contains everything, might not be fundamental at all, and might instead emerge from something deeper and more basic that has nothing to do with dimensions as we understand them. The stuff inside the room might actually be encoded on the walls. Before we go any further, let me be clear about what kind of claim this is. This isn't science fiction or speculation, but the result of serious theoretical work by accomplished physicists like Jacob Bekenstein, Stephen Hawking, Gerard Hooft, Leonard Susskind, and Juan Maldacena. The mathematics behind it is rigorous. The framework has been tested for internal consistency over decades, and aspects of it are now treated as established tools in theoretical physics. And here's where I need to be honest with you. These are theoretical frameworks we're discussing, not experimentally confirmed facts like the expansion of space observed through distant galaxies. The holographic principle emerges from the mathematics of black holes and quantum gravity, making claims about how fundamental degrees of freedom in a region might be organized. And while the explanatory power within certain theoretical contexts is enormous, extending these ideas to our actual cosmological space-time remains an active research area. I'm telling you this up front because understanding both the power and the current status of these ideas matters. What we're exploring is real physics, published in peer-reviewed journals and discussed at major conferences and taught in graduate programs worldwide. But it's also physics that's still being developed. The frontier hasn't stopped moving. If you're new to this channel, this is what we do here. Take the time to really understand ideas like this, sit with them, and let the strangeness sink in before moving on. If that sounds like your kind of journey, consider subscribing because it helps these videos reach more curious minds and tells me that deep exploration is what you want more of. Now, let's begin. Understanding the holographic principle requires starting somewhere that seems completely unrelated. Black holes, and specifically a question that occupied Jacob Bekenstein in the early 1970s. Entropy was the question. Entropy is one of those physics terms that shows up in different contexts, meaning slightly different things depending on who's talking. But for our purposes, think of it as a measure of how much information a system contains, or equivalently, how many different arrangements that system could have while still looking the same from the outside. A freshly shuffled deck of cards carries high entropy because the cards could be arranged in countless different ways, and you can't tell from looking at the deck which specific arrangement you're holding. A deck sorted by suit and number carries low entropy because there's essentially only one arrangement that qualifies as sorted. In physics, entropy connects to the number of microscopic states compatible with a given macroscopic description. So, a box of gas at a certain temperature and pressure could have its individual molecules arranged in an enormous number of different ways that all produce the same temperature and pressure readings. And that enormous number of possibilities relates directly to the entropy. And here's where Bekenstein enters the story. 1973 brought Bekenstein's paper Black Holes and Entropy. And in it, he asked a question that sounds strange at first. Do black holes have entropy? Consider what that question is really asking. A black hole, according to general relativity, is a region of space-time where gravity pulls so strongly that nothing, not even light, can escape once it crosses the event horizon. From outside, a black hole can be described by just three properties: mass, electric charge, and spin. That's it. Throw a library full of books into a black hole, or throw in a cloud of random gas, and the black hole settles down to a state described by those three numbers either way. Physicists call this the no-hair theorem, meaning black holes have no features that distinguish what went into them. They appeared to be the ultimate information destroyers. Bekenstein spotted a problem with this picture. Throwing high entropy material into a black hole where it simply vanishes would violate the second law of thermodynamics, because the total entropy of everything, the stuff thrown in plus the black hole plus everything else, should never decrease. If the information just disappears, entropy has gone down. His solution was radical. Black holes themselves must have entropy, and not just any entropy, but an entropy proportional to the area of their event horizon. Let me repeat that, because this is where everything starts. Black hole entropy is proportional to the area of the event horizon, not the volume inside, but the area of the surface. For ordinary objects, entropy scales with volume. So, twice as much gas means roughly twice as many possible arrangements and roughly twice the entropy. Bekenstein was claiming that for black holes, entropy scales with area instead. 1975 brought Stephen Hawking's paper that would cement this idea. Hawking demonstrated that black holes aren't perfectly black, that they emit thermal radiation, now called Hawking radiation, with a temperature determined by the black hole's properties. This meant black holes really do behave like thermodynamic objects with temperature and entropy, and the entropy really is proportional to horizon area. The formula that emerged from this work is called the Bekenstein-Hawking entropy formula. S equals Kb times A divided by 4 times the Planck length squared. S represents entropy. Kb is Boltzmann's constant. A is the event horizon area, and the Planck length is a fundamental length scale emerging from combining the gravitational constant, the speed of light, and Planck's constant. 1.61625 times 10 to the minus 35 meters. That's the Planck length. Roughly 6.36 times 10 to the minus 34 inches, or 5.30 times 10 to the minus 35 feet. 1 meter contains about 6.19 times 10 to the 34th Planck lengths, a scale so tiny that atoms look like galaxies by comparison. What strikes me about the Bekenstein-Hawking formula is what it tells us. The entropy, the amount of information, scales with area divided by Planck length squared. Knowing the maximum entropy a black hole can have means counting how many Planck area-sized cells fit on the horizon. I remember the first time I truly understood what this formula was saying, and I had to put down the book and just sit with it for a while. The implication is strange. All the information about what's inside a black hole, all the complexity and possible states, is somehow encoded on the surface, not in the volume. Black holes might seem like a special case because they're weird objects with extreme conditions near their horizons. And that's when physicists started asking, what if this isn't just about black holes? And what if it's telling us something fundamental about how information works in any region of space? Understanding why physicists generalized from black holes to everything requires thinking carefully about what the Bekenstein-Hawking formula really implies. Consider this thought experiment. You have a region of space, any region, and you want to know the maximum amount of information that can fit inside it. Your intuition says this should depend on volume, because more volume means more room for stuff and more information. Start packing that region with matter, adding more and more stuff and cramming in more and more information, and eventually something happens. Pack enough mass into a small enough region and you form a black hole. The matter collapses, an event horizon forms. And once that happens, the entropy of the region is given by the Bekenstein-Hawking formula, proportional to the area of the horizon. Here's the key insight. This sets an upper limit on how much entropy can fit in any region before it becomes a black hole. And that upper limit scales with area, not volume. Put another way, you might think you can cram unlimited information into a region by making the contents more and more complex. But there's a ceiling, and the surface area of the region determines that ceiling, not its volume. This observation led to something called the Bekenstein bound, which Bekenstein formulated in 1981. The Bekenstein bound says that for any bounded system with total energy E and effective radius r, there's a maximum entropy it can have. And this bound applies to any system, not just black holes. Before I tell you the numbers, take a moment to guess. How much information do you think can fit on a single square meter of surface, according to this bound. A terabyte? A billion terabytes? Something bigger? 1.38 times 10 to the 69 bits. That's what a single square meter of surface area can encode, according to the Bekenstein-Hawking relation. A 1 followed by 69 zeros. Here's how large that is. Counting to this number at 1 number per second would take far longer than the age of everything observable, because counting to 10 to the 18th alone would take about 31.7 billion years. And we're talking about 10 to the 69th. 1.28 times 10 to the 68th bits per square foot. 8.91 times 10 to the 65th bits per square inch. These numbers are so large, they're hard to contextualize. Every piece of digital information humanity has ever created, every photograph and video and document and piece of software, would fit many times over on a surface far smaller than a postage stamp, according to this fundamental limit. And this is where the holographic principle starts to take shape. 1993 brought Gerard 't Hooft's paper arguing that combining quantum mechanics with gravity forces you into a kind of dimensional reduction, where the fundamental degrees of freedom describing a region of space scale with the boundary rather than the volume. 't Hooft won the Nobel Prize in 1999 for his work on the Standard Model of particle physics. 1994 and 1995 brought Leonard Suskind's paper called The World as a Hologram, which developed and popularized this idea. Susskind argued that bulk physics, what happens inside a region of space, might be entirely encoded in boundary degrees of freedom, the physics on the surface surrounding that region. The name holographic comes from how holograms work. A two-dimensional piece of film that produces a three-dimensional image when illuminated properly, with full three-dimensional information encoded on a two-dimensional surface. Susskind and 't Hooft were suggesting something similar might be true of reality itself. The three-dimensional bulk, the space we seem to inhabit, might be entirely described by physics happening on a two-dimensional boundary. And here's where I need to address a common misconception, because this is important. Physicists saying holographic principle are not saying the world is an optical illusion, or that reality is fake, or that we're living in some kind of projected image. That misunderstands what hologram means in this context. What they're saying is more precise and more interesting. Two different physical descriptions, one involving gravity in a higher dimensional space, and one involving quantum mechanics on a lower dimensional boundary, might be exactly equivalent. They describe the same physics. Neither one is more real than the other, and they're dual descriptions of the same underlying reality. This isn't a statement that the world is an illusion. It's a statement about equivalence between seemingly different theories. And that equivalence carries implications for how we think about space, time, and information. The holographic principle remained a beautiful but abstract idea until 1997, when Juan Maldacena proposed a specific, concrete example that could be checked mathematically. This is called the ADS/CFT correspondence, one of the most influential ideas in theoretical physics over the past 30 years. Let me explain what ADS/CFT means, because understanding this correspondence matters for understanding why physicists take the holographic principle so seriously. ADS stands for anti-de Sitter space, a particular geometry of space-time. Unlike our observable space-time, which appears flat or slightly curved in a way consistent with de Sitter space, anti-de Sitter space has a negative cosmological constant and curves in the opposite way from what we observe on cosmic scales. Anti-de Sitter space has a peculiar property. It has a boundary. The space extends infinitely in certain directions, yet there's a well-defined boundary at infinity. And that boundary has one fewer dimension than the bulk. CFT stands for conformal field theory, a type of quantum field theory with special symmetry properties. Conformal field theories don't include gravity. They're quantum mechanical theories of particles and fields interacting according to specific rules. Here's what Maudethena proposed. A gravity theory in d+1 dimensional anti-de Sitter spacetime is exactly equivalent to a d-dimensional conformal field theory living on the boundary of that spacetime. Think about what this claims. On one side sits a theory with gravity, space-time curvature, and all the complexity of general relativity combined with quantum mechanics. On the other side sits a theory without gravity, living in one fewer dimension on the boundary. Maudethena was claiming these are the same theory. Not approximately the same, not similar in some limit, but exactly equivalent. Any calculation in one theory has a corresponding calculation in the other, and they give the same answers. The gravity theory was string theory in 5-dimensional ADS spacetime times a 5-dimensional sphere, written as ADS 5 times s to the power of 5. The boundary theory was a 4-dimensional conformal field theory called n=4 super Yang-Mills theory. Both are very specific, well-defined mathematical objects, and Maudethena claimed they describe the same physics. The paper caused an immediate sensation. Within months, Witten, Gubser, Klebanov and Polyakov had developed detailed dictionaries showing how to translate calculations from one side to the other. Calculations hard on the gravity side became easy on the field theory side, and vice versa. The duality turned out to be incredibly powerful. Over following years, thousands of papers explored different aspects of ADS/CFT. It was extended to other spacetimes, other theories, other boundary conditions. It was applied to everything from black hole physics to condensed matter systems to quantum information theory. Today, ADS/CFT is one of the most productive and influential ideas in theoretical physics, treated as a reliable tool by researchers worldwide. 2006 brought a formula that made the connection between geometry and quantum information explicit. Physicists Shinsei Ryu and Tadashi Takayanagi proposed what's now called the Ryu-Takayanagi formula, or RT for short, and it's become one of the central results in holography studies. Here's what RT says. In the boundary theory, the conformal field theory without gravity, you can calculate something called entanglement entropy. Entanglement is a quantum phenomenon where two parts of a system are correlated in ways that have no classical analog. And if you divide a quantum system into two parts, A and B, the entanglement entropy measures how much those parts are entangled with each other. Ryu and Takayanagi showed that in ADS/CFT, the entanglement entropy between a region A and its complement in the boundary theory can be calculated using a geometric quantity in the bulk. Find the minimal surface in the bulk that's anchored to the boundary of region A, and the entanglement entropy is proportional to the area of that minimal surface. Think about what this means. An information-theoretic quantity, entanglement entropy, measuring correlations in a quantum system, maps directly onto a geometric quantity, the area of a surface in a higher dimensional space-time. Geometry and information are connected. This result has been extended and generalized in numerous ways since 2006, shown to work in a wide variety of cases. And it suggests something striking. The geometry of space-time isn't a fundamental input to the physics. It's an output, emerging from the entanglement structure of the underlying quantum state. 2010 brought physicist Mark van Ramsdonk pushing this idea further. He argued that changing the entanglement pattern in the boundary theory changes the geometry in the bulk, and specifically that reducing entanglement between two regions makes the corresponding parts of the bulk more disconnected. At the extreme, if you have two completely unentangled systems, the corresponding bulk geometry isn't a single connected space-time. It's two disconnected pieces. Van Ramsdonk summarized this with a memorable phrase: "Space-time is built from entanglement." This is one of the parts that still amazes me, even after years of thinking about it. The geometric structure of space, the thing that feels solid and fundamental, the stage on which everything else seems to happen, might be woven from quantum correlations, from entanglement. If this picture holds, space-time isn't the fundamental arena. It's an emergent phenomenon, arising from something deeper and more basic, that has to do with information and quantum mechanics rather than geometry as we know it. And here's where things get complicated, and where I need to be careful about distinguishing what we know from what we're still figuring out. Everything described so far, the Bekenstein-Hawking formula, the holographic principle, ADS/CFT, the Ryu-Takayanagi formula, is well established within its domain. The mathematics is solid, internal consistency has been checked extensively, and ADS/CFT is treated as a working tool by thousands of physicists. There's a catch, though. Our actual cosmological space-time is not anti-de Sitter space. Looking out at observable cosmology, we don't see the negative cosmological constant characterizing ADS. Our space-time appears to have a small positive cosmological constant, making it more like de Sitter space than anti-de Sitter space, or, depending on how you interpret observations, it might be very close to flat. This matters because ADS/CFT is specifically a duality between gravity in anti-de Sitter space and a conformal field theory on its boundary. Extending holography cleanly to spacetimes that look more like our actual spacetime remains an active research area. Various proposals for de Sitter holography exist, but no single framework has achieved the status and acceptance that ADS/CFT enjoys. When physicists say space-time might be emergent or might not be fundamental, they're making an inference based on what works in ADS/CFT and related frameworks. They're saying that in these well-understood theoretical settings, space-time geometry can be reconstructed from boundary quantum information. And they're suggesting this might point to something more general that applies to our space-time too. Direct application to our cosmological space-time has not been established with the same rigor. This is frontier physics. The story isn't finished. Being honest about this matters. The holographic principle is not experimentally confirmed the way the existence of atoms is confirmed. It's a theoretical framework with enormous internal consistency and explanatory power, taken seriously by physicists worldwide, but it's also a framework still being developed, still being tested against its own predictions, still being extended to new domains. What we can say with confidence is this. In theoretical settings where holography has been most thoroughly studied, space-time geometry emerges from quantum entanglement on a boundary. The number of fundamental degrees of freedom scales with area, not volume. Information bounds are set by surfaces, not volumes. Whether this applies to the space-time we actually inhabit is one of the biggest open questions in fundamental physics. The story of holography didn't stop with ADS/CFT and the Ryu-Takayanagi formula. The field has been remarkably active, especially over the past decade. One major research thread connects holography to quantum error correction. 2014 and 2015 brought work from Almeri, Dong and Harlow showing that the relationship between bulk and boundary in ADS/CFT has the structure of a quantum error-correcting code. Error-correcting codes are familiar from classical computing, schemes for encoding information in a way that protects it from errors. If some bits get corrupted, the redundancy in the encoding allows recovery of the original information. Almeri, Dong and Harlow showed that bulk information in ADS/CFT is encoded in the boundary in a similar way. The information isn't localized simply, it's spread out with a kind of redundancy, allowing reconstruction of bulk physics from boundary data. This connection between holography and quantum error correction has become a major research area, suggesting that how space-time encodes information might have deep structural similarities to codes we use to protect quantum computers from decoherence. It also provides new tools for understanding how information is organized in holographic theories. The error-correcting structure tells you which boundary regions can reconstruct which bulk information, and it tells you about the limits of what can be computed from partial data. Quantum error correction is a field that arose from quantum computing. Quantum information is fragile. It can be corrupted by interactions with the environment, a process called decoherence. To build reliable quantum computers, you need to encode information in ways that protect it from errors. The key idea in quantum error correction is redundancy. You spread information across multiple qubits in such a way that even if some qubits get corrupted, you can recover the original information from the remaining qubits. What Almeri, Dong and Harlow showed is that the relationship between bulk and boundary in ADS/CFT has exactly this structure. Bulk information is encoded in the boundary like a quantum error-correcting code. Information isn't localized in a simple way, it's spread out with redundancy that allows reconstruction. This connection has become a major research area. It suggests the way space-time encodes information might have deep structural similarities to codes we use to protect quantum computers from decoherence. Another major development concerns black hole information. One long-standing puzzle in theoretical physics is what happens to information when it falls into a black hole. If black holes eventually evaporate through Hawking radiation, as Hawking showed in 1975, what happens to all the information that went in? Does it come out in the radiation? Does it disappear forever? For decades, this was called the black hole information paradox, and it remained unresolved. 2019 through 2021 brought a series of papers reviewed in a 2021 paper by Almeri and collaborators in Reviews of Modern Physics that made significant progress. These papers developed techniques for calculating the fine-grained entropy of Hawking radiation using what are called island calculations. The key result is that in certain models, the entropy of the radiation follows the Page curve, named after physicist Don Page, which is what you'd expect if information is being preserved and eventually comes out in the radiation. Initially, as the black hole evaporates, the entropy of the radiation increases, then reaches a maximum and decreases, ending up at zero or near zero when the black hole is fully evaporated. This is exactly what you'd expect if information is being transferred from the black hole to the radiation. These calculations are done in specific models and may not capture all features of real black holes, but they represent substantial progress on a problem that seemed intractable for decades. The field continues to develop. New connections are being found between holography and other areas of physics, from condensed matter physics to quantum computing. The holographic principle has become a lens through which physicists view questions about quantum gravity, the nature of spacetime, and the foundations of physics itself. Before going further, I want to address some things the holographic principle is not saying, because common misconceptions can lead people astray. The holographic principle is not saying we live in a computer simulation. This misconception comes up often, probably because both ideas involve information and seem to suggest reality might be encoded or computational in some way. Holography is a statement about mathematical equivalence between physical theories. It's not claiming anyone is running a simulation, not making claims about programmers or computers outside our reality. It's a statement about how fundamental degrees of freedom are organized, specifically that they scale with area rather than volume. The holographic principle is not saying reality is an illusion. When people hear hologram, they sometimes think of holographic images at science museums, where a 3D image appears to float in space, but is actually an optical trick. The holographic principle is not saying the three-dimensional world is a trick or illusion in this sense. It's saying there might be a dual description of the same physics, living on a surface mathematically equivalent to the bulk description. Both descriptions are equally real. Neither is more fundamental. They're different ways of talking about the same underlying physics. The holographic principle doesn't mean the boundary is the true reality while the bulk is somehow fake. In a duality, neither side is more real than the other. They're equivalent descriptions. Asking which one is really real is like asking whether a story told in English is more real than the same story told in French. They're different ways of expressing the same content. The holographic principle, as studied in theoretical physics, is not making claims about consciousness or spirituality or the holographic universe discussed in some popular contexts. Those are different concepts that happen to use similar vocabulary. The physics literature on holography is about information bounds, entropy, and dualities between quantum and gravitational theories. It's technical, mathematical, and precise. It doesn't involve speculations about minds or spiritual dimensions. I bring this up because I want you to appreciate the holographic principle for what it actually is. One of the most surprising and powerful ideas to emerge from theoretical physics, with rigorous mathematical foundations and implications for our understanding of space, time, and information. It doesn't need embellishment or mystification to be astonishing. The physics is remarkable on its own. The idea that the information content of a region scales with its boundary rather than its volume, that geometry might emerge from entanglement, that two seemingly different theories in different numbers of dimensions could be exactly equivalent, these are striking enough without adding layers of speculation about consciousness or spirituality. I've found that people sometimes want holography to mean more than it does, to connect to larger questions about meaning or purpose or mind. The physics doesn't go there. What it does go is somewhere equally strange and perhaps more verifiable, into the deep structure of space-time itself, into the relationship between information and geometry, into the fundamental organization of physical reality. That's enough. That's more than enough. The mathematics is pointing to something real and something strange, and following where it leads is a worthwhile endeavor, whether or not it connects to other questions we care about. Understanding what holography really claims requires understanding the Planck scale. The Planck length is the fundamental length scale emerging when you combine the three fundamental constants governing gravity, g, quantum mechanics, h bar, and relativity, c. Roughly 1.616255 times 10 to the minus 35 meters. In inches, about 6.36 times 10 to the minus 34. In feet, about 5.30 times 10 to the minus 35. These numbers are so small, they're almost impossible to visualize. So let me try giving you some sense of scale. 6.19 times 10 to the 34 Planck lengths fit in a single meter. The diameter of a proton, one of the smallest things we can measure directly, is about 10 to the minus 15 meters, 100 billion times larger than the Planck length. The Planck scale sits as far below the proton as the proton sits below roughly the size of a city. No technology exists, and none based on current physics can be conceived, that could directly probe the Planck scale. Our most powerful particle accelerators reach energies probing distances of about 10 to the minus 18 or 10 to the minus 19 meters. The Planck scale sits about 16 orders of magnitude smaller than that. This is why the holographic principle is a theoretical result rather than an experimental one. The physics it describes happens at scales so tiny that no experiment we can imagine would directly test it. Physicists rely on mathematical consistency, theoretical coherence, and indirect evidence instead. What's striking is that even though we can't directly probe the Planck scale, The Bekenstein-Hawking formula tells us this scale sets the fundamental pixel size for information on a surface. Asking how much information can fit on a given area means asking how many Planck area-sized cells fit on that area. 1.38 times 10 to the 69 bits per square meter. A sphere with Earth's radius, about 6,371 kilometers or 3,959 miles, could encode about 7.04 times 10 to the 83 bits on its surface, according to this purely geometric bound. These numbers sit so far beyond anything we could ever practically use that they might seem irrelevant. They're not. They're telling us something fundamental about the structure of reality, about how information is distributed, about what's possible in principle, even if not in practice. The numbers also tell us something about how much room physics has to work with. The gap between what humanity has achieved in terms of information storage and the fundamental limits is so vast that it's essentially unbridgeable. We're not going to run up against these limits. They're constraints on the structure of reality itself, not on technology. This is worth dwelling on. The holographic bound doesn't constrain us practically, but it constrains reality theoretically. It tells us that the universe has a specific information capacity, determined by geometry, set by the Planck scale. The universe isn't infinitely complex. It has a finite description, even if that finite description involves numbers we can't comprehend. This has philosophical implications. If the universe has finite information content, then, in principle, it could be described. The description would be impossibly long by human standards, but it would be finite. The universe is, in some sense, a finite object. Here's another perspective on what makes all this so strange: the relationship between geometry and information. In everyday experience, geometry and information seem like completely different things. Geometry involves shapes, sizes, distances, angles. Information involves data, patterns, knowledge. You can measure a room's dimensions without asking what information is stored there, and you can count bits in a computer without caring about the shape of the hard drive. Holography suggests that at a fundamental level, these are deeply connected. The geometry of space-time, the very structure of space and time, might be encoded in information, specifically in the entanglement structure of quantum systems. The Ryu-Takayanagi formula makes this explicit. Entanglement entropy on the boundary equals the area of a minimal surface in the bulk. Change the entanglement, change the geometry. This is what physicists mean when they say geometry might be emergent. It's not a fundamental input to the physics. It's an output arising from something more basic. What would that more basic thing be? In the holographic framework, it's quantum information, the patterns of entanglement between quantum degrees of freedom on a boundary. If this is correct, the question, what is space, has a surprising answer. Space isn't a stage on which physics happens. Space is a pattern of correlations, a geometry woven from quantum entanglement. I find this perspective genuinely awe-inspiring, Not because it tells us space isn't real. It is real, in the sense that it's a valid description of physics, but because it suggests that what we experience as the emptiness between things might arise from something as abstract and fundamental as information. Think about that for a moment. The space in this room, the distance from where you are to the wall, the volume of air between objects, all of this might be a manifestation of quantum correlations. The geometry might be woven from entanglement patterns that have nothing obvious to do with position or distance. This is what Van Ramsdonk meant when he said space-time is stitched together by entanglement. It's not a metaphor. In the holographic framework, it's a precise mathematical statement. Change the entanglement, change the geometry. Reduce the correlations, weaken the connections. Eliminate them entirely, and you have disconnected pieces of space rather than a unified whole. The distance between 2 points might, in some deep sense, be a measure of how entangled the corresponding boundary regions are. Closer things might correspond to more entangled regions. Farther things might correspond to less entangled regions. This isn't proven for our specific space-time, but it's how things work in ADS/CFT. If this picture extends to our world, then space as we experience it is an emergent property of quantum information. It's not a container for physics, it's a consequence of physics. It's not fundamental, it's derived. Let me walk through some key analogies physicists use to explain holography, because these can help build intuition for what's going on. The most common analogy gives holography its name, the hologram. In a real hologram, a two-dimensional piece of film encodes a three-dimensional image. Illuminate the film properly, and you can see depth, look around objects, and perceive a full three-dimensional scene. In the holographic principle, the boundary, a lower dimensional surface, encodes the bulk, a higher dimensional spacetime. The physics of what happens inside a region can be fully described by physics happening on the boundary of that region. I want to be careful with this analogy because it can mislead. A real hologram is a projection, an image that appears but isn't physically there the same way real objects are. The holographic principle isn't saying the bulk is an illusion. It's saying the bulk has a dual description in terms of boundary physics. Both descriptions are equally valid. Neither is more real. Another analogy is the blueprint versus the building. Architectural blueprints, two-dimensional drawings, can fully specify a three-dimensional building. All the information about the building's structure is contained in the plans. Holography suggests all the information about the bulk might be contained in the boundary. The boundary is like the blueprints. The bulk is like the building. This analogy has limits too. Blueprints and buildings are different things. In holography, boundary and bulk descriptions are two ways of describing the same physics. There's no separate building existing independently of the blueprints. A third analogy I find helpful is the library on a surface. Normally, you'd think a bigger library holds more books, because more volume means more storage. Holography says the maximum storage is determined by the walls of the library, not the volume inside. It's as if all books have to be registered on a surface around the library, and that surface sets the limit. Each analogy captures part of the holographic idea, but none captures all of it. The mathematical structure of ADS/CFT and related dualities is richer and more precise than any analogy can fully convey. Analogies help build intuition as long as we remember their limitations. A fourth analogy worth mentioning is the MRI scan. When doctors take an MRI, they build a three-dimensional image of your body from a series of two-dimensional slices. The full 3D structure is inferred from lower dimensional data. Holography has a similar flavor. Higher dimensional structure inferred from lower dimensional information. In holography, though, the relationship isn't inference or reconstruction in the usual sense. It's exact duality. The boundary theory isn't data from which you deduce the bulk. It is the bulk, described differently. What holography means for how we think about physics and reality is often overlooked in discussions. Throughout physics history, we've repeatedly discovered that our intuitive picture of reality is incomplete or misleading. The Earth isn't the center of everything. Space and time are intertwined. Matter is mostly empty space. Particles can behave like waves. Holography might be another step in this process. Our intuition says space is a container. More volume means more capacity. And the fundamental description of reality should involve things happening inside a region. Holography suggests the fundamental description might live on the boundary instead. Area, not volume, sets the limits. The inside might be encoded on the outside. This doesn't mean our intuitions are worthless, because they work fine for everyday life and for most of physics. When we push to the extremes, to black holes and quantum gravity and the Planck scale, our intuitions can fail. The mathematics leads to conclusions that feel wrong but might be right. What's striking is that physicists can make progress in these regimes at all. We can't do experiments at the Planck scale and can't directly test holography. We can do mathematics, check internal consistency, and ask whether different calculations give the same answers. When they do, that's evidence we're onto something real. The human capacity to push into these domains, using mathematics as a guide when senses and intuitions fail, is itself something worth pausing to appreciate. We're talking about the structure of reality at scales far removed from anything we can directly experience. Yet we can reason about it, formulate precise claims, and check them. Let's return to black holes, because they're where this all started, and recent developments have continued to make them central to the story. As I mentioned earlier, one long-standing puzzle concerns what happens to information that falls into a black hole. Hawking showed in 1975 that black holes emit thermal radiation and eventually evaporate. But thermal radiation by its nature doesn't carry detailed information about what went in. It's random, like heat coming off a stove. This led to what's called the black hole information paradox. Throw a book into a black hole, wait for the black hole to evaporate into thermal radiation, and where did the information in the book go? Was it destroyed? Does it come out in the radiation somehow, in a way too subtle to detect? For decades, this remained an open question. Hawking initially argued information was destroyed, which would violate quantum mechanics where information is preserved. Most physicists were reluctant to accept this, but couldn't prove him wrong. The holographic principle was always central to attempts at resolving this paradox. If bulk physics is encoded on a boundary, the information that fell in should still be encoded somewhere. It shouldn't be lost. The recent island calculations provided a new way to think about this. Using techniques developed from holography and quantum gravity, physicists showed that in certain models, the entropy of Hawking radiation follows a curve, the Page curve, consistent with information being preserved. The calculations involve finding islands, regions inside the black hole that contribute to the entropy of the radiation in a specific way. This is technical and model dependent, but the upshot is that holographic ideas are providing tools to make progress on a puzzle that seemed intractable for decades. Information might not be destroyed after all, and might be encoded in the radiation in a way consistent with quantum mechanics. Let me go back to 1973, to Jacob Bekenstein, and fill in more details about the moment when this line of thinking started. 1973, and theoretical physics sat at a crossroads. General relativity, Einstein's theory of gravity, had been around for nearly 60 years. Quantum mechanics, the theory of the very small, had been enormously successful for even longer. Both theories worked brilliantly in their own domains, but they didn't fit together. Applying quantum mechanics to gravity produces nonsense. Infinite answers, contradictions, mathematical breakdown. This is the problem of quantum gravity, unsolved today despite enormous progress in understanding it. Black holes sit right at the intersection of these two theories. Massive objects where gravity dominates, yet quantum effects turn out to be crucial for understanding what happens at their boundaries. Jacob Bekenstein, then a graduate student at Princeton working under John Wheeler, started thinking about a seemingly simple question. What happens when you drop things into a black hole? Classical general relativity gave a clear answer. The stuff falls in, crosses the event horizon, and is gone. The black hole might increase in mass, but that's it. From outside, you can't tell whether a black hole formed from the collapse of a star made of hydrogen or helium or heavy elements. Once it settles down, it's characterized by just three numbers: mass, charge, and spin. This is the no-hair theorem. Bekenstein spotted a problem. Take a box of gas at some temperature. That gas has entropy, a measure of its disorder, of the number of microscopic arrangements consistent with its macroscopic state. Now drop the box into a black hole. According to classical general relativity, the entropy just disappears. The gas is gone, swallowed by the black hole. And black holes in the classical picture have no entropy. This violates the second law of thermodynamics. Total entropy of a closed system should never decrease. You can't make entropy disappear just by dropping it into a hole. Bekenstein's insight was that black holes must have entropy. Thinking carefully about what would happen if you tried violating the second law using black holes, he figured out that the entropy must be proportional to the horizon area. The argument goes like this. If you could decrease total entropy by dropping high entropy stuff into a black hole with zero entropy, you'd violate thermodynamics. To prevent this, the black hole must have entropy of its own, and that entropy must increase when you add stuff. The only quantity that increases, depending on what you add, is the horizon area, since adding mass increases the event horizon radius. The entropy must be proportional to the area. 1973, when Bekenstein first proposed this, brought controversy. Many physicists were skeptical. Black holes were supposed to be simple objects, characterized by just a few numbers. How could they have entropy, which implies a huge number of microscopic states? The answer came 2 years later from Stephen Hawking. Hawking had initially been skeptical of Bekenstein's proposal. He had done calculations that seemed to show black holes couldn't have temperature, which relates to entropy. A black hole at equilibrium with its surroundings would have to emit radiation to have a temperature, and black holes, by definition, don't emit anything. And then Hawking did a more careful calculation, taking quantum mechanics into account, and found something striking. Near the event horizon of a black hole, quantum effects allow pairs of particles to be created from the vacuum. This is a real quantum effect, happening everywhere in space all the time. Normally, these particle pairs immediately annihilate each other. But near a black hole horizon, something different can happen. One particle of the pair can fall into the black hole while the other escapes. The escaping particles carry energy away from the black hole. This energy must come from somewhere, and it comes from the black hole's mass. Over time, the black hole loses mass and shrinks. To an outside observer, it looks like the black hole is emitting radiation. Hawking showed this radiation is thermal, meaning it has a specific temperature determined by the black hole's properties. This is Hawking radiation, and its discovery transformed understanding of black holes. Black holes aren't completely black. They glow faintly with thermal radiation. They have temperature. Because they have temperature, they must have entropy. Hawking's calculation confirmed Bekenstein's proposal and gave us the exact formula. S equals K under B times A divided by 4 L under P squared. Entropy equals Boltzmann's constant times the horizon area divided by 4 times the Planck length squared. This formula is striking for several reasons. First, it confirms that black hole entropy scales with area, not volume. Second, it involves the Planck length, a scale combining gravity, quantum mechanics, and relativity. Third, it gives specific, calculable numbers. Let me put numbers on this to help appreciate the scale. Consider a black hole with mass equal to our Sun. Its event horizon would have a radius of about 3 kilometers, roughly 1.86 miles. The surface area would be about 113 square kilometers, about 44 square miles. 10 to the 77th power in units of Boltzmann's constant. That's roughly the entropy of this black hole according to the Bekenstein-Hawking formula, a 1 followed by 77 zeros. For comparison, the entropy of all the visible stars in our galaxy, all their thermal radiation and particle content combined, is estimated to be much smaller. A black hole with the mass of a single star has more entropy than all the stars together. Black holes are the most entropic objects in known theories of physics. Their entropy is determined entirely by their surface area. This is a striking result that deserves emphasis. You might think the stars, with all their nuclear reactions and complex dynamics, would carry the most entropy. Black holes beat them by many orders of magnitude. The reason comes back to the area scaling. A black hole packs the maximum possible entropy into its region, and that maximum is set by the horizon area. The fact that entropy maxes out at black holes, and that maximum scales with area, is what drove the theoretical developments that followed. It's what made physicists think that area scaling might be telling us something fundamental, not just about black holes, but about information in general. 1977 brought Stephen Hawking and Gary Gibbons extending these ideas in an important direction. They showed that similar thermodynamic properties apply to cosmological horizons, not just black hole horizons. Cosmological horizon is a different kind of boundary. In the universe that's expanding, like ours, there's a limit to how far you can see. Light from very distant objects has been traveling since the beginning, but space has been expanding the whole time. Beyond a certain distance, expansion carries objects away faster than their light can reach you. This creates a horizon around every observer. Gibbons and Hawking showed this cosmological horizon also has thermodynamic properties. It has temperature. It has entropy. The entropy is proportional to the area of the horizon. This was important because it suggested the area-entropy connection isn't specific to black holes. It might be a general feature of horizons in gravitational physics. Jumping forward to the 1990s brings us to when the holographic principle was explicitly formulated. Gerard 't Hooft is a Dutch physicist who won the Nobel Prize in 1999 for his work on the Standard Model of particle physics. 1993 brought his paper Dimensional Reduction in Quantum Gravity, arguing that something fundamental was going on with the area scaling of entropy. 't Hooft's argument went like this. In quantum gravity, we expect fundamental degrees of freedom to be governed by some quantum theory. Normally, you'd expect the number of degrees of freedom in a region to scale with volume. More volume, more places to put stuff, more degrees of freedom. The black hole entropy formula contradicts this. Maximum entropy in a region can't exceed the Bekenstein-Hawking entropy of a black hole fitting in that region. That maximum scales with area, not volume. 't Hooft concluded the fundamental theory of quantum gravity must have fewer degrees of freedom than you'd naively expect. Degrees of freedom must scale with the boundary, not the bulk. There's a kind of dimensional reduction happening. The effective number of dimensions is one less than you'd think. Leonard Susskind at Stanford picked up this idea and ran with it. 1994 and 1995 brought his paper The World as a Hologram, laying out the holographic principle explicitly. Susskind argued that any theory of quantum gravity consistent with the Bekenstein-Hawking formula must be holographic in the following sense. Physics of a d plus one-dimensional bulk must be equivalent to physics on a d-dimensional boundary. Bulk physics is projected onto the boundary. The name holographic comes from the analogy with holograms. But Susskind was careful to note this isn't saying the world is an optical illusion. It's saying there's mathematical equivalence between descriptions in different numbers of dimensions. This was a bold claim, still somewhat abstract. It would take another few years before a concrete example was found. 1997 brought that concrete example. Juan Maldacena's paper on ADS/CFT. Let me take a moment to explain what anti-de Sitter space is and why it's important, because this helps you understand what Maldacena proposed. Space-time can be curved in different ways. The curvature depends on matter and energy content, and also on a parameter called the cosmological constant. Positive cosmological constant gives you de Sitter space, a space-time that expands exponentially. Our actual cosmological space-time appears to have a small positive cosmological constant, which is why expansion is accelerating. Negative cosmological constant gives you anti-de Sitter space, a space-time with negative curvature, shaped like a saddle at every point. It doesn't correspond to our actual cosmology, but it has mathematical properties making it very useful for theoretical work. One key property of anti-de Sitter space is that it has a well-defined boundary at spatial infinity. The space extends forever in some directions, yet there's a boundary where geometry approaches a specific form. That boundary has one fewer dimension than the bulk. Maldacena's proposal was specific. He identified a particular gravity theory in a particular anti-de Sitter spacetime and showed it should be exactly equivalent to a specific conformal field theory on the boundary. The gravity theory was string theory in 5-dimensional ADS spacetime times a 5-dimensional sphere, ADS 5 times s to the power of 5. The boundary theory was a 4-dimensional conformal field theory called n equals 4 super Yang-Mills theory. Both are very specific, well-defined mathematical objects. Maldacena claimed they describe the same physics. This was a concrete realization of the holographic principle. The 5-dimensional bulk with gravity was equivalent to the 4-dimensional boundary without gravity. Information in the bulk was encoded on the boundary. The paper caused an immediate sensation. Within months, Witten, Gubser, Klebanov and Polyakov had developed detailed dictionaries showing how to translate calculations from one side to the other. Calculations hard on the gravity side became easy on the field theory side, and vice versa. The duality turned out to be incredibly powerful. Over following years, thousands of papers explored different aspects of ADS/CFT. It was extended to other spacetimes, other theories, other boundary conditions. It was applied to everything from black hole physics to condensed matter systems to quantum information theory. Today, ADS/CFT is one of the most productive and influential ideas in theoretical physics, treated as a reliable tool by researchers worldwide. What makes ADS/CFT striking from a conceptual standpoint deserves attention. On the gravity side sits a theory with space-time and curvature. Objects move through space-time along curved paths. Black holes form and evaporate. Geometry is dynamic, responding to matter and energy it contains. On the field theory side sits a quantum theory without gravity. There is no curved space-time. Particles interact according to quantum mechanics rules. But there's no gravitational force, no event horizons, no Hawking radiation directly. These are the same theory. A black hole forming in the bulk corresponds to a specific pattern of excitations in the boundary field theory. Temperature and entropy of the black hole correspond to temperature and entropy in the field theory. Evaporation of the black hole corresponds to decay of the excitations. Every physical process in the bulk has a corresponding process in the boundary. The translation is exact. Neither description is more real than the other. They're two ways of talking about identical physics. This is one of the most striking features of ADS/CFT. You might expect that having gravity would make a theory fundamentally different from one without gravity. Gravity curves space-time, creates horizons, allows black holes. A theory without gravity seems like it would be missing these features entirely. What ADS/CFT says is that all those gravitational phenomena are present in the boundary theory, just described differently. A black hole in the bulk is a thermal state in the boundary. Hawking radiation is thermalization of boundary excitations. The event horizon is a particular pattern of entanglement. Everything is there, just translated into different language. This suggests that gravity itself might be emergent. Not that it's not real, it is real, in the same way that temperature is real, but that it might be a derived property rather than a fundamental one. Gravity might emerge from the same quantum mechanics that governs the boundary theory. This is what makes the holographic principle so revolutionary. It's not just saying that information scales with area. It's suggesting that one of the fundamental forces of physics, gravity, might be an emergent phenomenon. Space-time and gravity together might arise from quantum mechanics without gravity. This equivalence is what physicists mean when they say space-time might be emergent. Space-time in the bulk, with its geometry and extra dimension, can be reconstructed from the boundary theory. It's not a fundamental input, it's an output of boundary physics. The extra bulk dimension has an interesting interpretation. In the boundary field theory, there's a parameter describing energy scale or coarseness of the description. At high energies, you probe short distances. At low energies, you see only coarse-grained features. This energy scale maps onto the extra dimension in the bulk. Moving deeper into the bulk corresponds to moving to lower energies, longer distances in the boundary. The extra dimension of space isn't something foreign to the boundary theory. It's encoded in the boundary theory's structure, emerging from how the boundary theory organizes information at different scales. This brings us to one of the most striking connections discovered in recent years, the relationship between geometry and entanglement. Entanglement is a quantum phenomenon with no classical analog. When two quantum systems are entangled, their states are correlated in ways no classical mechanism can explain. Measuring one system immediately affects what you'll find when measuring the other, even if they're far apart. Einstein called this spooky action at a distance, and used it to argue quantum mechanics must be incomplete. Experiments have consistently confirmed entanglement is real. It's a fundamental feature of quantum mechanics. In the ADS/CFT context, Ryu and Takayanagi discovered in 2006 that entanglement entropy in the boundary theory has a beautiful geometric interpretation in the bulk. Let me explain what they found. Divide the boundary theory into two regions, A and its complement, B. Entanglement entropy, SA, measures how entangled region A is with region B. This is a purely information-theoretic quantity, calculable from the quantum state of the boundary theory. Ryu and Takayanagi showed that in ADS/CFT, this entanglement entropy equals the area of a specific surface in the bulk, the minimal surface anchored to the boundary of region A, extending into the bulk. An information-theoretic quantity, entanglement entropy, equals a geometric quantity, area of a surface. Information and geometry are connected by a precise mathematical relationship. The formula is SA equals area of minimal surface divided by 4g, where g is Newton's gravitational constant. The resemblance to the Bekenstein-Hawking formula is not coincidence. The Bekenstein-Hawking formula can be understood as a special case of Ryu-Takayanagi, when the minimal surface is the black hole horizon itself. This result has been extended and generalized enormously since 2006. Corrections for quantum effects exist. Time-dependent versions exist. Versions applying to more general spacetimes exist. The core insight remains. Geometry in the bulk encodes entanglement in the boundary. Van Ramsdonk's 2010 paper, Building Up Spacetime with Quantum Entanglement, pushed this connection to its logical conclusion. Van Ramsdonk asked, what happens if you change the entanglement structure of the boundary theory? What happens to the bulk geometry? Reducing entanglement corresponds to weakening geometric connectivity of the bulk. If two boundary regions are highly entangled, corresponding bulk regions are connected by spacetime. Reducing entanglement weakens that connection. At the extreme, if two parts of the boundary are completely unentangled in a product state, the corresponding bulk isn't a single connected spacetime. It's two disconnected pieces. Van Ramsdonk summarized this dramatically. Spacetime is stitched together by entanglement. More entanglement means more connection. Less entanglement means less connection. Geometry of space emerges from the pattern of quantum correlations. This has implications worth pausing on. If spacetime geometry emerges from entanglement, then the structure of space itself is a quantum phenomenon. Space isn't a backdrop for quantum mechanics, it's a consequence of quantum mechanics. This is one of those results that, when I first understood it, made me stop and think for a long time. Empty space between things, distances separating objects, geometry of it all, might be woven from quantum correlations, from entanglement. Let me pause and offer an interactive moment. Think about a room you're familiar with. Now imagine all the information about what's inside that room, the arrangement of furniture, the air molecules, everything, could, in principle, be encoded on the walls of the room. Not in the walls, on the walls. on the two-dimensional surfaces bounding the three-dimensional space. The volume inside would then be like a projection, a reconstruction from boundary data. Three dimensions you experience would emerge from information stored in two dimensions. Does that seem impossible? Counterintuitive? It should. Everyday experience tells us the inside of a room is very different from its surface. You fit more stuff by expanding volume, not by expanding walls. The mathematics of black holes and quantum gravity keeps pointing to this area scaling. Maximum information scales with the surface. Geometry emerges from the boundary. Sit with that for a moment before we continue. Information in physics isn't just a human concept. It's a physical quantity. The arrangement of particles, the state of fields, the configuration of matter and energy, all of this is information. Information has to obey physical laws. One of the deepest principles in physics is that information is conserved. In quantum mechanics, this is encoded in unitarity of evolution. Quantum states evolve in a way preserving all information. Nothing is ever truly lost. This seems to conflict with black holes. Throw a book into a black hole, and the black hole eventually evaporates into random thermal radiation. And where did the information go? This is the information paradox discussed earlier. The holographic principle provides a framework for understanding how information is organized in ways that seem impossible from a naive perspective. The information isn't lost, it's encoded differently than expected. In ordinary physics, we assume information is located where things are. If a book is in a room, information about the book is in that room, in that volume of space. Holography suggests a different picture. Information might be organized by boundaries, not volumes. Information about what's inside might be encoded on the surface. This challenges our intuitions about locality. We're used to thinking that if something happens here, it affects things here first and only later affects things far away. Information is local. Causes are local. Effects propagate outward from where causes happen. Holography suggests locality might be emergent rather than fundamental. The fundamental description might be non-local in surprising ways. Information about the bulk might not be localized in the bulk at all. It might be spread across the boundary in patterns that only look local when you translate them back into bulk language. This is a radical shift. It means the intuition that things happen in specific places, that information is stored in specific volumes, might be a consequence of how we perceive reality rather than a feature of fundamental reality itself. How exactly bulk locality emerges from boundary physics, and when it fails to emerge, are active questions. The direction of answers is clear. Our intuitions about where information lives and how it's organized may need revision. The error-correcting structure discovered by Almheri, Dong and Harlow helps explain how this works. Bulk information isn't stored at specific boundary points. It's encoded redundantly across the boundary, like a quantum error-correcting code. This redundancy is what allows bulk physics to look local even though the fundamental description is on a boundary without the bulk's extra dimension. This is a radical shift. It means locality, the idea that things affect other things through local interactions at neighboring points, might be emergent rather than fundamental. The fundamental description might be non-local in surprising ways. How exactly bulk locality emerges from boundary physics, and when it fails to emerge, are active questions. The direction of answers is clear. Our intuitions about where information lives and how it's organized may need revision. The Bekenstein bound deserves more exploration for what it tells us about the relationship between energy and information. Bekenstein formulated this bound in 1981, relating entropy to energy and size. The Bekenstein bound says that for any bounded system with total energy E and effective radius r, entropy is limited by S is less than or equal to 2 pi times kb times E times r divided by h bar times c. In bits, bits is less than or equal to 2 pi times E times r divided by h bar times c times ln2. Here's a concrete example to make this tangible. Take 1 kilogram of matter with equivalent energy E equals mc squared, about 9 times 10 to the 16th joules, contained within a sphere of radius 1 meter, about 3.28 feet. 2.58 times 10 to the 43 bits. That's the maximum this system can contain according to the Bekenstein bound. That's a 1 followed by 43 zeros. Enormous by human standards. Far more than all data humanity has ever created. Still a limit. Notice, this limit depends on both energy and size. More energy, higher limit. Bigger size, higher limit. Still a limit. The Bekenstein bound and Bekenstein-Hawking formula are related but distinct. The area-based formula applies specifically to black holes. The Bekenstein bound applies to any system. Both point to the same conclusion. Information is bounded. Reality is finite. 1999 brought the covariant entropy bound, when physicist Raphael Bousso proposed a more general formulation of the holographic entropy bound. His version, called the covariant entropy bound, or Bousso bound, uses light rays to formulate the bound in a way working in any spacetime. The key idea: instead of looking at a surface and asking how much entropy can fit inside, construct a light sheet, which is the set of all light rays going inward from the surface. Entropy on that light sheet is bounded by the area of the original surface. This formulation is more general because it works even in curved spacetime, even when the notion of inside and outside is ambiguous. It's a statement about how information can be distributed along light rays emanating from a surface. 2002 brought Bousso's major review of the holographic principle, bringing together all these ideas: black hole thermodynamics, entropy bounds, and the emerging holographic framework. The covariant formulation was important because it showed the holographic bound wasn't just a peculiarity of special cases. It applies quite generally in a wide variety of space-time geometries. This universality is part of what makes physicists take the holographic principle so seriously. Let me return to the Ryu-Takayanagi formula and explore some implications more deeply. Remember, RT says entanglement entropy in the boundary theory equals the area of a minimal surface in the bulk. This formula has been extended in numerous ways. One extension handles time-dependent situations. The original RT formula applies to static configurations. But what about dynamical situations where things are changing? 2007 brought Hubeni, Rangamani and Takayanagi, proposing a covariant extension handling time-dependent cases. Another extension involves quantum corrections. RT gives the leading term in a certain expansion. Including quantum effects in the bulk gives corrections to this formula. These corrections have been worked out and tested. All these extensions continue to work. The connection between geometry and entanglement isn't an accident or artifact. It's robust under generalizations. This suggests the geometry-entanglement connection is something deep. It's not just a feature of one particular model. It seems to be telling us something fundamental about how geometry and information are related. Imagine two boxes, A and B, with some quantum system inside each. If the systems are entangled, they're correlated in ways that can't be explained classically. According to holography, at least in ADS/CFT, geometry of the bulk depends on entanglement between boundary regions. If A and B are highly entangled, corresponding bulk regions are well connected by spacetime. If A and B are unentangled, bulk regions are disconnected. What happens if you slowly reduce entanglement between A and B? Van Ramsdonk argued the bulk connection weakens. Spacetime between the regions becomes less connected, in a technical sense that can be made precise in the mathematical framework. At the limit, with zero entanglement, you have two separate pieces of spacetime. They're not connected at all. This is a strange picture. It suggests connectivity of spacetime, whether two regions are connected by space at all, depends on quantum correlations between boundary systems. If entanglement creates connection, then spacetime itself is a manifestation of quantum correlation. I've thought about this result many times, and it still strikes me as striking. Empty space between things might be held together by entanglement. Geometry might be stitched from information. The implications extend beyond abstract physics. If spacetime emerges from entanglement, then the classical picture of reality, where space provides a fixed background and things move through it, is fundamentally misleading. Space isn't a stage. Space is part of the show. Space emerges from the same quantum mechanics that governs particles and fields. This suggests a kind of unification that's different from what physicists traditionally sought. Instead of unifying forces, like electromagnetism and the weak force, holography suggests unifying space itself with the quantum mechanics that describes matter. They're not separate. They arise together from the same underlying structure. What that underlying structure looks like in detail is still being worked out. But the direction is clear. Look to quantum information, to entanglement patterns, to the organization of correlations. That's where spacetime comes from. What holography means for the concept of dimensions deserves attention before we close. We live in 3 spatial dimensions and 1 time dimension, for a total of 4 dimensions in the usual counting. This seems fundamental. You can move in 3 perpendicular directions and time flows through it all. Holography suggests the number of dimensions might not be as fixed as we think. In ADS/CFT, a theory in D plus 1 dimensions is equivalent to a theory in D dimensions. The extra dimension isn't really extra. It's encoded in the boundary theory. This raises a question. Is our 4-dimensional spacetime the fundamental description, or is there a 3-dimensional or lower dimensional description encoding everything we see? We don't know the answer. As I've emphasized, our spacetime isn't ADS, and extending holography to our actual cosmology is an open problem. The possibility is intriguing. If there is a lower dimensional encoding of our spacetime, then the 4th dimension, in the sense of the extra bulk dimension, would be emergent. It would arise from some structure in the boundary theory, just as the radial direction in ADS arises from energy scale in the CFT. This is speculative, and I want to be clear about that. It's the kind of speculation grounded in rigorous mathematical examples. We know it can happen, we're just not sure whether it does happen for our particular spacetime. The possibility that our spacetime has a holographic description is intriguing enough to drive significant research. If it's true, then everything we experience, all the distances and volumes and spaces, would be encodable on some lower dimensional surface. The 3 dimensions we navigate would be a way of organizing information that's fundamentally stored differently. This wouldn't make our experience less real. The 3 dimensions would still be accurate descriptions of physics in the regimes where we operate. They would just be emergent rather than fundamental. Like temperature, which is real and useful but emerges from molecular motion, space might be real and useful but emerge from quantum information. The research continues. Proposals for de Sitter holography are being developed. New techniques are being tried. The mathematical tools are advancing. Whether a clean holographic description of our cosmological spacetime will be found remains to be seen. But the search itself is pushing the boundaries of what we understand about the structure of reality. Holography connects to other areas of physics in surprising ways. One surprising application has been to condensed matter physics, the study of materials and their properties. Certain strongly correlated materials, like high-temperature superconductors, are very hard to study using conventional techniques. Interactions are too strong for standard approximations. ADS/CFT provides an alternative approach. By mapping the condensed matter system onto a gravitational dual, when such a mapping exists, you can use gravitational techniques to calculate properties that are otherwise intractable. This is called applied holography, or holographic condensed matter, and it's become a significant research area. It doesn't mean superconductors are really black holes or anything like that. It means mathematical tools developed for one problem can be useful for another, even if physical systems are completely different. Holography also connects to quantum information and quantum computing. The error-correcting structure of ADS/CFT has inspired new approaches to quantum codes. Ideas from holography about how information is organized have influenced thinking about quantum complexity and computational complexity. Physics has a way of being interconnected. Ideas developed in one area turn out useful in others. The holographic principle, starting with questions about black holes, has branched out to touch areas as diverse as materials science and computer science. This interconnectedness is itself evidence that holography is touching something real. Ideas that are merely mathematical tricks don't usually have such wide-ranging applications. Ideas that capture something about the structure of reality tend to show up everywhere, because reality is all of a piece. The fact that the same mathematical structures appear in black hole physics, quantum information theory, condensed matter physics, and computer science suggests that these fields are looking at the same underlying reality from different angles. Holography provides a unifying framework that connects them. This is one of the markers of deep physics. When an idea explains multiple phenomena across different domains, when it keeps showing up in unexpected places, when different approaches keep converging on the same conclusions, that's evidence you're on to something real. Holography has all these features. Where does all this leave us? The holographic principle is one of the most striking ideas to emerge from theoretical physics in the past 50 years. It suggests the way we think about space, information, and dimensions might need revision. It provides specific, testable, within the theoretical framework, predictions, checked extensively. It continues to yield new insights and applications. At the same time, it remains a theoretical framework. Direct application to our cosmological spacetime is still being worked out. The Planck scale, where these ideas become relevant, sits far beyond experimental reach. We're using mathematics and theoretical consistency as guides, because direct observation isn't available. This is frontier physics. It's exciting precisely because questions are so fundamental and answers so surprising. We're not just filling in details, we're questioning the basic structure of reality. Whether spacetime is really emergent in our particular case, whether the holographic principle applies beyond the ADS context, whether we'll ever find ways to test these ideas directly, these are questions for the future. Research continues. Mathematics is being developed. New ideas are being explored. And that, to me, is part of what makes physics beautiful. We don't have all the answers. We're still learning. The story is unfinished. Let me walk through the historical timeline one more time, because seeing the progression of ideas helps appreciate how we got here. 1973, Jacob Bekenstein publishes Black Holes and Entropy, proposing black holes have entropy proportional to horizon area. This is the beginning. 1975, Stephen Hawking publishes Particle Creation by Black Holes, showing black holes emit thermal radiation. This confirms black holes have temperature and entropy. The Bekenstein-Hawking formula is established. 1977. Gibbons and Hawking extend horizon thermodynamics to cosmological horizons, showing the ideas apply beyond black holes. 1981. Bekenstein formulates the universal upper bound on entropy to energy ratio for bounded systems, another step toward general entropy bounds. 1993. Gerard 't Hooft argues for dimensional reduction in quantum gravity, laying conceptual groundwork for holography. 1994 to 1995. Leonard Susskind develops and popularizes the world as a hologram, articulating the holographic principle explicitly. 1997. Juan Maldacena proposes ADS/CFT, providing a concrete, mathematically precise example of holography. 1998. Witten and others developed the dictionary for ADS/CFT, showing how to translate calculations between bulk and boundary. 1999. Raphael Bousseau proposes the covariant entropy bound, generalizing holographic bounds to arbitrary spacetimes. 2002. Bousseau publishes a comprehensive review of the holographic principle, bringing together various threads. 2006. Ryu and Takayanagi propose their formula relating boundary entanglement entropy to bulk surface areas, making the geometry information connection explicit. 2010. Mark van Ramsdonk articulates the idea that entanglement creates space-time connectivity. 2014 to 2015. Almheri, Dong and Harlow connect holography to quantum error correction. 2019 to 2021, island calculations provide new tools for addressing the black hole information paradox. Nearly 50 years of development, from Bekenstein's original insight about black hole entropy to sophisticated holographic tools we have today. The progress has been striking. The questions remain deep. Let me talk about where this all stands today and what the open questions are, because clarity about what's established versus what's still being figured out matters. Within the theoretical physics community, several things are widely accepted. Black hole thermodynamics, the Bekenstein-Hawking entropy formula, and Hawking radiation are well-established results in semigravity. The calculations have been redone many ways, and the answers are consistent. Black holes behave like thermodynamic objects with temperature and entropy, and the entropy is proportional to the horizon area. ADS/CFT is broadly used as a non-perturbative definition of certain quantum gravity theories. Thousands of papers have been written using this duality. It's treated as a reliable tool, not speculation. Entanglement-based geometry tools, like the Ryu-Takayanagi formula and its extensions, are central to the field. They've been checked extensively and are used routinely in calculations. What's still being developed is the application of these ideas to our actual cosmological spacetime. Our spacetime is not ADS. Extending holography cleanly to de Sitter or flat spacetimes is an active research area. Various proposals exist, but none has achieved the status and acceptance of ADS/CFT. The degree to which spacetime is emergent in a precise, general sense, beyond the ADS/CFT context, is also still being worked out. The evidence within ADS/CFT is strong. Extending this to a general claim about all spacetimes is a harder problem. Connecting holographic ideas to direct empirical tests remains challenging. Most support for holography comes from theoretical consistency and indirect successes rather than direct measurement. This is to some extent inevitable, given that relevant physics happens at the Planck scale. The holographic principle sits in an interesting position. It's not a speculative idea floating without support. It has rigorous mathematical foundations, extensive internal consistency checks, and has led to real progress on long-standing problems like black hole information. It's also not a confirmed experimental result. It's a theoretical framework physicists take very seriously because of its power and coherence, even though direct experimental verification remains out of reach. I want to close by returning to the big picture and thinking about what all of this might mean. If the holographic principle captures something fundamental about reality, space and time might be effective concepts that emerge from deeper quantum degrees of freedom. Three-dimensional space we perceive, the time that flows, might arise from patterns of information and entanglement that don't inherently have anything to do with geometry as we experience it. This is a shift in perspective worth sitting with. It suggests that when we ask, "What is space?" the answer might not be an empty container or a fabric that can be curved. The answer might be a pattern of correlations, a description that emerges from something more basic. It also highlights something about human knowledge. We can reason about these domains. We can ask questions about the fundamental structure of reality, use mathematics to explore possibilities, and arrive at answers that, while counterintuitive, have internal coherence and predictive power. The ability to reason about the Planck scale, about information bounds, about emergent geometry, is itself remarkable. These are domains that have nothing to do with human survival, nothing to do with our evolutionary heritage, nothing to do with the world our brains evolved to navigate. Yet we can think about them, we can make progress, we can discover things. This suggests that the mathematical structure of reality is, in some sense, accessible to human minds. Not easily accessible, not intuitively accessible, but accessible through careful reasoning and mathematical analysis. The universe seems to be organized in ways that mathematics can capture, and human brains can do mathematics. Why this should be the case is itself a deep question. Why should the universe have mathematical structure at all? Why should that structure be discoverable by beings like us? These questions don't have clear answers. But the success of physics, including the success of holographic ideas, suggests that there is something to discover, and we can discover it. The holographic principle started with a question about black holes. Do they have entropy? 50 years later, that question has led us to contemplate the possibility that space-time itself is emergent, that the inside is encoded on the outside, that geometry might be woven from entanglement. Whether this picture will ultimately prove to be the correct description of our actual observable space-time remains to be seen. Research continues. Mathematics is being extended. New approaches are being tried. Regardless of how the story ultimately resolves, the journey has revealed something important. The structure of reality is far stranger than everyday intuitions suggest. And yet, strange as it is, we can understand it. We can write it down. We can check it. That, to me, is one of the most striking things about being human. We find ourselves in a reality that operates by rules we didn't choose and couldn't have guessed. With patience and careful thought, we can discover those rules. We can understand them. We can see, dimly perhaps, how deep the rabbit hole goes. If you've made it this far, thank you for taking this journey with me. These ideas take time to absorb, and there's no rush. Let them sit. Come back to them. Think about what it would mean if space really does emerge from information. The next time you're standing in a room, looking at the walls around you, remember that according to some of the most sophisticated physics we know, those walls might be where the real action is. The information about everything inside might be encoded on the boundary. The volume might be the hologram. Does holography mean we're living in a simulation? This question comes up often, probably because both ideas involve reality being encoded in some sense. They're very different ideas, though. The simulation hypothesis asks whether our reality is a computation running on some external computer, whether there's a programmer or computer outside our reality generating what we experience. Holography doesn't say anything about that. Holography is about equivalence between physical theories, saying a gravity theory in d+1 dimensions is equivalent to a non-gravitational theory in d dimensions. Neither theory is more real than the other. Neither is a simulation of the other. They're dual descriptions of the same physics. Holography is about the structure of physics, not about whether physics is real or simulated. It's telling us how information is organized, not whether someone is processing that information. The two ideas use similar vocabulary, which causes confusion. They're making very different claims. Holography doesn't say anything about consciousness or the nature of mind either. Some popular accounts mix holographic ideas with speculations about consciousness, suggesting the holographic universe connects to how minds work or how awareness arises. As far as the physics is concerned, holography is about entropy bounds, dualities between theories, and emergence of geometry from quantum information. It's technical and mathematical. It doesn't make claims about consciousness. This isn't to say consciousness isn't interesting, or that connections between physics and mind might not someday be found. Those connections haven't been established. Holography, as understood by physicists, isn't making claims in that direction. I mention this because being clear about what the science actually says versus what gets added in popular accounts matters. The physics is remarkable on its own, without embellishment. Let me give you one more scale perspective to sit with. 7.04 times 10 to the 83 bits. That's the maximum information that could fit on a sphere with Earth's radius, 6,371 kilometers or 3,959 miles, according to the Bekenstein-Hawking relation. That's information on the surface of an Earth-sized sphere. Not inside the sphere, on the surface. All information humanity has ever created, every book, every photograph, every video, every scientific paper, every email, everything, is estimated at around 10 to the 22nd bits. Maybe 10 to the 23rd bits if you're generous. Maximum information on an Earth-sized surface is 10 to the 83rd bits. That's about 60 orders of magnitude more. The ratio between these numbers is hard to even conceptualize. If every bit of human-created information were a single atom, and you wanted to compare that to 10 to the 83 atoms, you'd find that 10 to the 83 atoms is far more than the estimated 10 to the 80 atoms in the observable cosmos. The holographic bound sits so far beyond anything we could ever approach that it's essentially infinite from a practical perspective. It's not actually infinite, though. It's a specific number, determined by fundamental physics. This tells us something about the structure of reality. It's finite, but the numbers are so large that finiteness doesn't impose any practical constraint. We'll never fill up the storage capacity of a spherical surface, let alone approach the fundamental limits. Here's another way to think about the numbers. If you could count one number per second, how long would it take to count to 10 to the 69th power, roughly the number of bits per square meter? At one number per second, 10 to the 9th seconds is about 31.7 years. 10 to the 12th seconds is about 31,700 years. 10 to the 15th seconds is about 31.7 million years. 10 to the 18th seconds is about 31.7 billion years, longer than observable history from the Big Bang. And we're trying to reach 10 to the 69th power. You'd need to count for 10 to the 69th seconds. There aren't enough seconds from now until everything ends to come close. These numbers are beyond comprehension in a deep sense. We can write them down and manipulate them mathematically, but we can't really picture them. They're too large. Physics gives them to us anyway. The holographic bound tells us reality has this structure, this capacity, this mathematical form. We discover things we can't fully imagine. This is part of what makes theoretical physics humbling and exhilarating at the same time. We can calculate things we can't picture. We can reason about scales and structures that have no counterpart in everyday experience. The mathematics takes us places our intuitions can't follow. The Planck scale is the most extreme example. It's so far from human experience that it might as well be imaginary, except that it appears in our equations with specific, calculable consequences. The holographic bound tells us that Planck scale physics constrains the information content of reality. We can't see it, can't probe it, can't directly detect it, but we can reason about it. We can derive consequences. We can check those consequences against other parts of physics. This is how physics works at the frontier. Direct observation isn't always possible. Mathematics becomes the primary tool. You trust the mathematics because it's been checked many ways, because different approaches give the same answers, because the framework is coherent. Holography is mathematics at the frontier. It's telling us things about Planck-scale physics, about the organization of information, about the emergence of geometry that we can't directly verify. We take it seriously because the mathematics is solid, because the framework works, because it connects to things we can check. Whether it will someday be directly testable, we don't know. For now, it's the best theoretical framework we have for understanding certain deep questions about the structure of reality. When I first encountered the holographic principle, I was skeptical. The idea that the inside could be encoded on the outside, that area could trump volume, seemed too strange to be right. My intuition rebelled. And then I started working through the arguments. Bekenstein's reasoning about entropy, Hawking's calculation of radiation, the mathematical structure of ADS/CFT, the checks and cross-checks. Slowly, my intuition shifted. Not because I could visualize it better, I'm not sure anyone can really visualize holography, but because the logical structure became clear. The pieces fit together. The mathematics was consistent. Different approaches gave the same answers. This is how physics often works. You can't directly observe quarks, or visualize 11-dimensional string theory, or picture the quantum wave function. You can follow the arguments, check the math, and see whether the framework is coherent. Holography passes these tests. It's coherent and consistent. It makes specific predictions within the theoretical framework that have been checked. Physicists take it seriously, not because it feels intuitive, it doesn't, but because it works. One of the lessons of holography is humility about our intuitions. Our intuitions are shaped by evolution. They're adapted to the world of medium-sized objects, moving at medium speeds, the world our ancestors needed to navigate. They're not adapted to black holes, quantum mechanics, or the Planck scale. When our intuitions clash with mathematics, and the mathematics has been checked and rechecked and turns out consistent, we should probably update our intuitions rather than reject the mathematics. This is hard. Intuitions feel real. They feel like they're telling us about the world, but they're really telling us about how our brains model the world, which is not the same thing. Holography asks us to imagine the inside of a region is encoded on its boundary. That area trumps volume. That geometry emerges from entanglement. None of this feels right. The mathematics is coherent, and the framework works. Sometimes the world is stranger than we can easily imagine. That's okay. We can still reason about it. We can still understand it. We just have to let go of the expectation that understanding will feel intuitive. There's something deeply human about the story of holography. For thousands of years, people have looked at the world and tried to understand its structure. We've moved from thinking the Earth was the center of everything to understanding we're on a small planet orbiting an ordinary star in one of hundreds of billions of galaxies. Along the way, we've discovered that reality doesn't match our intuitions. The Earth seems flat. It's not. Space seems absolute. It's not. Time seems to flow the same for everyone. It doesn't. Matter seems solid. It's mostly empty space. Holography suggests another revision. Space itself might not be fundamental. 3 dimensions we experience might emerge from something lower dimensional. Geometry might be woven from information. The inside might be encoded on the outside. Each of these discoveries required trusting mathematics over intuition, following the logic even when it led to strange conclusions. Each time, the strange conclusions turned out correct. This pattern, intuition failing and mathematics succeeding, is one of the most striking features of physics. We can reason about things we can't directly experience. We can discover truths that senses and intuitions wouldn't have led us to. Holography is part of this tradition. It's mathematics pointing toward a structure we never would have guessed. Whether it's the final answer or a step towards something else, it's part of the ongoing human project of understanding reality. I'd like to take one more moment to discuss what the holographic principle means for how we approach fundamental questions. For centuries, physics proceeded by finding the fundamental constituents of things and understanding their interactions. Atoms, then particles, then quarks and leptons. The assumption was that if you found the smallest pieces and knew how they interacted, you'd understand everything. Holography suggests a different kind of fundamentality. It's not about finding the smallest pieces in a spatial sense. It's about finding the right description, which might not involve spatial intuitions at all. In ADS/CFT, the fundamental description is arguably the boundary CFT, which has no gravity and one fewer dimension. You could also say the bulk gravity theory is fundamental. They're equivalent. The notion of fundamental has shifted from made of the smallest pieces to most economical description or deepest equivalence. This shift in what fundamental means is worth pausing on. For most of physics history, fundamental meant small. Find the smallest building blocks and you've found what's fundamental. Atoms, then subatomic particles, then quarks and leptons. Each level revealed smaller components of the previous level. Holography suggests something different. Fundamental might not mean smallest. Fundamental might mean the description from which other descriptions can be derived. In that sense, the boundary description might be fundamental because the bulk can be derived from it. Or the bulk might be fundamental because the boundary can be derived from it. Or neither is more fundamental than the other because they're equivalent ways of describing the same physics. This changes how we think about reductionism, the idea that explaining complex things means breaking them into simpler components. Holographic duality suggests that sometimes there are multiple equally valid ways to decompose a system, and none is privileged as the true decomposition. This is a conceptual shift as significant as any in the history of physics. We're not just discovering new particles or forces, we're questioning the framework within which particles and forces make sense. One of the things I find most compelling about holography is how it connects seemingly disparate areas. Black hole thermodynamics, which started as a niche topic in gravitational physics, turned out to be connected to quantum information theory. The study of space-time geometry turned out to be connected to entanglement. Abstract mathematical dualities turned out to have implications for condensed matter physics. This interconnectedness suggests we're touching something real. Holographic ideas aren't isolated curiosities. They're part of a web of connections linking different parts of physics together. When different lines of inquiry converge on the same conclusions, that's a sign you're onto something. Holography has seen striking convergence. Black hole entropy, quantum gravity, string theory, quantum information, all pointing toward the same basic ideas about information, area, and emergence. The philosophical implications deserve careful framing. If holography captures something fundamental, it suggests space and time might be effective concepts. They might emerge from deeper quantum degrees of freedom. The geometry we experience might be a pattern arising from more basic structures. This is a significant shift in how we think about physics. Traditionally, we've assumed space-time is the stage on which physics happens. Particles and fields live in space-time. Laws of physics are written in terms of what happens at different points in space-time. Holography suggests this might be backwards. Space-time might not be the stage. It might be part of the performance. It might emerge from the quantum state rather than being a precondition for the quantum state. This doesn't mean space-time is unreal or illusory. It's real in the sense that it's an accurate description of physics in many regimes. It might not be fundamental, though. It might arise from something deeper. What would that deeper thing be? In the holographic picture, it's quantum information. It's the entanglement structure of quantum degrees of freedom on a boundary. Geometry of space encodes and is encoded by patterns of correlation. If this is correct, the most basic description of reality might not involve space and time at all. It might be purely quantum mechanical, purely information theoretic. Space and time would then be emergent phenomena, like temperature is emergent from the motion of molecules. I find this perspective both humbling and awe-inspiring. Humbling because it suggests our intuitions about space and time might be misleading us at a fundamental level. Awe-inspiring because it suggests questions about the nature of space and time might have answers, might be tractable, might yield to mathematical analysis. There's another aspect worth touching on, what holography says about limits of information. The Bekenstein-Hawking bound tells us there's a maximum amount of information that can fit in a region of space. And that maximum is determined by the surface area. For ordinary objects, we're nowhere near this limit. A hard drive stores information using magnetic domains on a disk. The density is impressive by human standards, but it's nothing compared to the fundamental limit. 8.91 times 10 to the 65 bits per square inch. That's how much information can fit on a square inch of surface, according to the Bekenstein-Hawking relation. For comparison, a modern hard drive stores maybe 10 to the 12th bits per square inch. The fundamental limit is about 50 orders of magnitude higher. We will never approach the fundamental limit with any technology based on ordinary matter. The limit comes into play only for systems so dense they're about to become black holes. For any normal system, we're so far from the limit that it's essentially infinite. The existence of the limit is what matters here. It tells us information, at a fundamental level, is finite. There's only so much that can be encoded in a given region. The description of reality is finite, not infinite. This has implications for debates about whether reality is continuous or discrete, whether there's a smallest scale of structure. The holographic bound suggests that at some level, things are finite. Information is bounded. The journey of understanding holography is ongoing. Researchers around the world work on extending these ideas, testing them, finding new applications. Some work on de Sitter holography, trying to extend the ADS/CFT framework to spacetimes more like our actual cosmology. Some explore connections between holography and quantum computing, using insights from one field to advance the other. Some work on the black hole information problem, using island calculations and related techniques to understand how information is preserved. Some probe the emergence of space-time, trying to understand more precisely how geometric structure arises from quantum entanglement. The field is alive and active. Questions are deep, and progress, while sometimes slow, is real. Physics is an ongoing conversation between humans and the mathematical structure of reality. We ask questions, we do experiments when we can, and mathematics when we can't. We follow the logic wherever it leads. Holography is one of the strangest places that logic has led. A description where the boundary contains the bulk, where entropy scales with area, where geometry emerges from entanglement. Whether this is the final picture or a stepping stone to something else, it represents a genuine insight into the structure of reality. It's not speculation or philosophy, it's physics, grounded in specific mathematical claims that can be checked. The journey from Bekenstein's 1973 paper to sophisticated holographic tools we have today demonstrates human curiosity and intellectual persistence in remarkable ways. People followed the mathematics. They asked hard questions. They developed new frameworks when old ones weren't sufficient. And they discovered something striking. The world might be organized in ways we never imagined. What would it mean for something to be fundamental? If space can be derived from information on a boundary, is space fundamental? Is information fundamental? Or is fundamental not the right way to think about it? What does it mean for two theories to be equivalent? In ADS/CFT, a gravity theory and a field theory describe the same physics, but they're very different theories with different numbers of dimensions. One has gravity, the other doesn't. How can they be the same? What would it mean if our space-time turned out to be holographic? Not ADS, but our actual cosmological space-time. If a lower dimensional description encoded everything, how would that change our understanding of the world? These are not questions I can answer definitively. They're questions to sit with, to turn over in your mind, to revisit as you learn more. Let me offer a final reflection. When you look around at the world, you see space. 3 dimensions extending in every direction. Up and down, left and right, forward and back. It seems obvious, seems fundamental. Physics is teaching us to be cautious about what seems obvious. The Earth seems flat. It's not. The Sun seems to go around the Earth. It doesn't. Time seems absolute. It isn't. Space itself might not be what it seems. 3 dimensions around you might emerge from something deeper. Geometry might be woven from information. The inside might be encoded on the outside. This is strange. It's counterintuitive. It challenges assumptions about what's fundamental and what's derived. It's also beautiful. The idea that quantum information, entanglement, correlation, might give rise to the geometry of space carries an elegance that's hard to articulate. It unifies things that seemed separate. it reveals hidden connections. Whether this picture is ultimately correct, we don't know yet. Research continues. Even if details change, the journey has been striking. From black holes to holography, from entropy to emergence, physics has taken us to places we never expected. Thank you for taking this journey with me. These ideas deserve time to settle, to percolate, to be revisited. Don't rush through them. Let them sink in. The next time you walk through a room, remember what we've discussed. The walls might contain more than you think. The boundary might encode the bulk. The surface might hold the secrets of the volume. If you found this exploration worthwhile, consider subscribing to the channel. There are more journeys like this, more questions about the nature of reality that reward patience and curiosity. Sleep well under the stars. Whatever space-time is, you're part of it. However the boundary encodes the bulk, you're in there somewhere. However information gives rise to geometry, you're information too. The world is strange and beautiful and mysterious. We're fortunate to be able to understand even a little of it. Every generation of physicists has pushed the boundaries of what we know. From Newton's laws to Maxwell's electromagnetism to Einstein's relativity to quantum mechanics, the story has been one of successive revolutions in understanding. Each revolution revealed that reality was stranger than the previous generation had imagined. Holography might be the next revolution, or it might be a step toward one. Either way, it's part of the ongoing human endeavor to understand the structure of reality. We ask questions, follow the mathematics, check our answers, and slowly, incrementally, we learn. The holographic principle reminds us that this endeavor is far from complete. We don't yet know the fundamental structure of space-time. We don't know if space is emergent. We don't know if the information content of our region is bounded by its surface. These are open questions, and their answers might reshape our understanding of everything. What we do know is that the mathematics keeps pointing towards surprising conclusions. Information scales with area. Geometry connects to entanglement. Different theories in different dimensions can be equivalent. The boundary might encode the bulk. These are strange claims, but they're grounded in rigorous physics. They've been checked many ways. They keep yielding new insights. They're part of our best current understanding of the deep structure of reality. And that understanding continues to develop. The story isn't finished. Good night.